Welcome to Primary Aspects number 145. In this podcast, we are looking at the aerodynamics of high-speed trains in crosswinds. We'll go through the general aerodynamics as to how certain modifications affect the lift, side force, and rolling moment, including how the nose of the train affects these values. And to do that, we'll be looking at a paper called Numerical Studies on Aerodynamics of High-Speed Railway Trains Subjected to Strong Crosswinds. So you can find this in the link in the description. It's open access, so you can play along at home. So there are a couple interesting things to look at when looking at high-speed trains in crosswinds. The first is that for a crosswind to deviate from an almost aligned train, it needs to be quite strong, because if the train is moving fast, then the vector diagram to give the resulting wind direction means that the crosswind needs to be strong. So if, for example, you had your train going at 300 kilometers per hour, but the wind was only like 30 kilometers per hour coming from the side, directly side on, when you do the vector diagram, it's still not going to be that much. It might only be a few degrees deviation. So to get a significant deviation for this entire wind, you need to have quite a strong crosswind. And as such, these winds are less common than just everyday winds. But then there's another aspect you can think about, which is that if a train is moving faster, then the aerodynamic forces become greater because the lift and side forces are proportional to the velocity squared. So that makes the high-speed train operation fairly unique. And as such, there is potential for a strong crosswind to create enough force on a high-speed train to make it unsafe. And that's what these researchers are investigating in this paper. So these researchers are looking into CFD usage for this paper, and one thing that's really cool about this is that they're using a one-to-one model. So one of the main reasons why they say they want to use CFD for this investigation is because if you were to use a wind tunnel, for example, trying to use a one-to-one scale train is almost impossible. I mean, there's no wind tunnel on Earth that's big enough, so you have to go for a model. So using CFD, though, you can get away with this one-to-one model and look at the general effects quite easily. So that's why they used the CFD here. That's the only practical application. So unfortunately, they used RANDs for this study, which, while this is better than a poke in the eye, it means that we will be lacking the finer details, including any transient phenomena. So RANDs really just averages everything out, so that's what we'll see. So let's look at this high-speed train model they are investigating. So we have in figure 1 here, the general model they are using is called a TMC-M-TMC train. This is a funny acronym, but it's quite logical because the entire train consists of 3 separate compartments, so 3 vehicles they call it. Each train is like a little compartment or a carriage. So there is the TMC section at the front and at the back of the train, so we have this front part here, and then at the back they just have this exact same compartment, just reversed. Then in the middle they have the M compartment, which is this middle bit here. And for those of you just listening to this, you can watch the video on Spotify and or YouTube, but I'll describe the CAD to you. So the front and back is like a typical train where you have the nose section, which is slightly slanted, and they do check out a few different slant angles. But then the middle carriage is really just like this rectangular prism. There's no slants to the front or rear faces. So interestingly, from this view, the front of the high-speed train isn't really that pointed as I mentioned in this picture. The nose is angled a little, but not nearly as much as other high-speed trains like the Shinkansen in Japan. The front and rear parts of the train, which are called TMCs, are 24.4 meters long, while the middle compartment which is called an M compartment, is 22.8 meters long. So the entire train is 71.6 meters long, which is why we mentioned earlier that trying to put this in a wind tunnel is impossible. So that's why they use CFD. The TMC and M compartments are 3 meters wide and are 0.8 meters from the ground and extend up to 3.855 meters from the ground, so that high. In addition to this, these researchers looked at 4 different high-speed train noses, and the effects of these train noses on the effects of the crosswind at different angles, on the lift coefficient, side forces, and rolling moment coefficients, not pitching moment, rolling moment. So in addition to this, they show in table 1, they have the dimensions of the 4 noses, and let me scroll to figure 2 so we can see them here. So the H dimension is simply the height, the L1 dimension is the distance from the bottom of the nose to the bottom of the end of the nose, and then the L2 distance is the distance from the top of the nose, like when you go to the top of the on top of the train, the front of the nose, all the way to the back of the nose when you're on top. So these 2 lengths here change effectively how slanted the front nose is. We also have H, which is the height of the vehicle, and then W, which is the width of the vehicle. So these 4 configurations result in different nose angles, and we have the different dimensions here. So they range, the width is always 3 meters, so it stays as a constant. L2, which is the distance on top of the train from the front of the nose to the rear of the nose, always stays at 0.46 meters. Whereas L1, which is the distance from the bottom of the nose, like the front bottom nose, to the rear of the bottom of the nose, is either 1.6 meters or 3 meters, and the height ranges from 2.6 meters to 3 meters. So looking at all of these different configurations, and if you do the math, you'll find out that the sleekest nose angle is about 45 degrees, while the most upright angle is about 69 degrees, and the other two configurations fall within that range there. So let's move on to the CFD setup now. So I'm not really sure what the domain size is, because they say something that's quite interesting that I don't quite understand. I'll say it word for word. They say, in order to facilitate the change of wind direction, regular 24 angular prisms with a radius of 250 meters and 50 meters in height are established in the whole circulation domain with the train model in the center. So I think they're talking about the domain size here. I think from this excerpt, what they mean is that the domain is a circular domain with a radius of 250 meters, and then the height is 50 meters. This makes a lot of sense, because if you have a circular domain, you can then specify the wind angle quite easily and not have to worry about separation on the corners of the domain. So I think the domain is 500 meters in diameter, which is huge, but obviously the train is 71 meters long, so it's not that big in comparison, and the height is 50 meters, so that's quite tall. The train itself is only like 3 or 4 meters high off the ground. So the grid is structured, which means that the cells are uniform blocks. They're not prisms, which means that the domain is very ordered. So the benefit of meshing your domain with a structured mesh, so you can see here in figure 3, you have all these blue lines. Those are, I'll zoom in a little bit actually. That's a structured mesh. So this extends out into the domain as well. And the main advantage of the structured mesh is that you don't use fewer cells. So you don't have to have like all these weird angles and like prisms and whatever that are just going into small cavities. You can just use these blocks, and that reduces how many cells you can use to get the same kind of mesh. The downside of using the structured mesh is that you don't capture the finer details of the geometry nor the flow physics as well. So that's a trade-off between a structured and unstructured mesh, and pretty much all CFD solvers have these two different options. So overall, this domain has 2 million cells with a minimum grid spacing of 0.1 meters. So 0.1 meters is not very fine, but then again, we have a train which is 71 meters long, so relatively speaking, it's quite fine. Now, one thing that's interesting is that they use a non-slip wall for the walls, which is an interesting approach, because yes, the wind flowing along the ground, which is also a wall, will produce a boundary layer, but the wind that the train is feeling is not just the wind from the atmosphere, but also from its own motion. So as you like have the train going along, obviously it goes at 200 kilometers per hour, whatever, and the wind is not actually moving compared to it's not moving, the train is moving through the wind. Then you have on top of that the crosswind. So the boundary layer will be thicker here because they have the entire ground as a non-slip, and then you have the entire wind going along, like the wind from the crosswind plus the like relative motion between the train and the wind and the air coupled into that as well. So the boundary layer should be thicker than what it will be in reality, unless I'm reading their setup incorrectly, but I don't think I am. So that means that this non-slip boundary condition for the ground is not that accurate. In reality, you could either correct for this by making the ground a moving ground condition, or by altering the coefficients in the turbulence model, the former way being much easier than the latter way. So if you were to just have the moving ground condition for the ground, then what would happen is you would have a relative difference in velocities between the oncoming wind and the ground itself. That would then simulate the crosswind, and then the moving ground itself simulates the motion of the train compared to just ambient air, or the tracks, or whatever you want to call it. Like that's the reference frame. So anyway, so the turbulence model that they use, because they are using a RANS setup, which means they have to use a turbulence model, is the K epsilon realizable, which is okay but not great. You know, it's more towards the dodgier end than the really good end. The mesh independent study was quite interesting though. So if we go down a little bit, we have the model validation a bit here, but if we go up, we have the mesh validation around here somewhere. Here we go. So a mesh independent study is used to make sure that the resolution of your mesh is adequate. The way we usually do this is by making 3 meshes ranging from coarse to fine, and then one in between. Each mesh should be significantly finer than the last, and a good rule of thumb is that there should be twice as many cells in the next mesh than the previous mesh. So the coarsest mesh, let's say you have 1 million cells, the next level up, which is like the medium fineness, would be 2 million, and then the finest mesh would be 4 million. So that's a good way of determining whether your mesh is independent or not. So in this mesh independent study, the researchers only used 2 meshes. The first had 1.52 million cells, and the second had 2 million cells. This is a 33% refinement, which is better than nothing, but it should really be more. And the reason why is because if you have a small change in the number of cells, then you don't really get a very accurate idea as to if your mesh has converged or not. However, the more interesting thing is that they say that the difference in the lift coefficients between these 2 resolutions was very small. I'm not really sure what very small means. It's a qualitative statement. I'm not sure what the quantitative actual result is, whether this is 0.1% difference, 1% difference, or even 5% difference. But whatever it is, they just say it's very small. So they're saying it's validated. So I'm not sure what that means. But so let's assume that this difference was only 0.1%, which means that the mesh is quite nice. What this also means is that potentially the mesh that they then end up using was overkill, because we don't know how few cells we need to still get the same result. They only looked at 2 different cells meshes, which we had 1.5 million and 2 million cells. If we went down to 1.3 million, for example, do we still get a very similar lift force coefficient? So that's why we need to have 3 different mesh levels usually to begin with. So the reason why having 3 different levels of refinement is better, because ideally the coarsest level is significantly different to the medium refinement, but then the medium refinement is very close to the fine refinement. So that would then give us a good idea as to how many cells we really need to get an accurate simulation. And this may not be such a big deal if you're only running a few simulations, but in this study where they had almost 30 simulations, they could have saved a lot of time by finding the lowest number of cells and then gone without, instead of going with like 1.5 million or 2 million cells. That's additional cells that you don't really need, and that increases computational time. So another interesting thing to note is that this mesh independent study was performed at a wind yaw angle of 90 degrees. That means that the wind was coming directly from the side, and I'm not sure why this configuration was chosen as the mesh independence configuration, but it's interesting. It might just be because it was the most extreme. So the mesh independent study was interesting. It's generally speaking decent. I mean, there's only one thing that I'm not too sure about, which is when they say that the deviations of the lift force coefficients between different mesh sizes are very small. What that very small is, I'm not too sure. As for the number of cells, if you wanted to make this a more efficient process, you could have gone for like a coarser mesh and see if that you can get away with that still and reduce the number of cells that you need, and then it'll make it quicker. So anyway, the researchers investigated wind angles from 0 degrees to 90 degrees with 15-degree increments, making it 7 different crosswind configurations from 0 degrees, 15 degrees, 30 degrees, 45, 60, 75, and 90. To validate this CFD, the researchers used some data from a wind tunnel experiment. However, that experiment was on a British train and not this one. This one is like a high-speed train in China, whereas this other one is a British train in Britain. So they're relatively similar geometries though, but they do differ a little bit. In figure 6, we see the comparison here. So for the validation, the blue line is for the experimental data, the red line is for this CFD, and we see the lift and rolling moment coefficients for the 2 different types of trains for different wind yaw angles. The CFD results give the exact same trends as experimental data, namely that when the wind's yaw angle increases, the lift coefficients increases dramatically. Also, as the wind's yaw angle increases, the rolling moment coefficient also increases, as you can see here. And it's a little surprising just how much the yaw angle affects the lift coefficient. I mean, at a 0 degree angle at a 0 degree yaw angle, these trains produce no lift. But as the yaw angle goes up to 90 degrees, so completely perpendicular to the trains, these trains produce a lift coefficient of 0.9, which is really good considering that this is not an airfoil. Some airfoils don't even produce this much lift. Granted, they're not very good airfoils, but still these airfoils are airfoils and they're not trains, and this train produces more lift than some of these airfoils. And it's interesting because when you think about a train, like from a side-on point of view, it's quite bluff. So to have the train producing this much lift, it's possibly just because the flow hits the train, then it like goes over the top, and it and it separates, so you have just low pressure generally speaking there. Underneath you have the railway and the tracks, so there's not much going on there in terms of flow physics, at least chaotic flow physics, and so we just get a pressure difference which then results in this lift. I'm not too sure, we don't have flow vis for this, but that might be why we get such a high lift coefficient for these trains. It's very very interesting and very amazing. So another interesting thing is that the lift production is fairly linear with yaw angle. So as we just double the yaw angle, the lift production kind of doubles. So we can conclude that the general trends are definitely validated. As for the actual values, there is no way to tell. The error could be 1% or even 10%, because we first of all we have different trains, and secondly, the CFD, again, we're using rands, and we don't know if like what the very small deviations in that lift coefficient between the different meshes meant. Anyway, let's move on to the results. So in figure 7, we get some pretty cool surface pressure measurements on the train with different yaw angles. As expected, as the yaw angle increases, more and more pressure is felt on the windward side, so the side that the wind is like crashing into. And what's more, less and less pressure is felt on the nose of the train. So as the wind comes around from the front of the train to the side of the train, there's less and less pressure on the nose, which makes sense. So these two results are very expected, because when the wind is hitting the side more and more and not the front, there is more deceleration of the flow, and hence a higher static pressure on the side facing the wind more. So effectively, whichever side is facing the wind is going to be feeling a higher pressure, because you have all that kinetic energy from the dynamic pressure being converted into pressure we can feel on the surface. So if you don't know the difference between static pressure, dynamic pressure, and total pressure, check out this video here, which is or actually, if you're on Spotify, actually you should probably go to YouTube and go to our Aero Fundamentals videos and type in dynamic pressure, static pressure, and total pressure, and you'll find that video. I was going to put a little card here, but if you're watching Spotify, you can't click the card, so check that on YouTube instead to get that video, which tells you the difference between dynamic pressure, static pressure, and total pressure. So let's go down to figure 8, where we see the variations in the aerodynamic force on the train under different wind yaw angles. This is on the effects of the lift and side force and rolling moment coefficients. So when it comes to the side force and rolling moment coefficients, the front compartment is definitely affected the most with both of these quantities. And the lift coefficient, which is generally speaking affected across all different 3 compartments, rises steadily with increasing yaw angle from 0 degrees, in terms of the lift coefficient, side force coefficient, and rolling moment coefficient, to about 0.9 when the wind is at a 75-degree yaw angle, and then it drops slightly at 90 degrees. So in other words, the side force coefficient, lift force coefficient, and rolling moment coefficient all start at 0 when the yaw angle is 0, and as you increase it to 90 degrees, they all pretty much increase by the same amount to about 0.9, 0.8. So that's quite interesting that they all hover around the same amount, just the coefficient. So the side force and rolling moment coefficients of the middle and rear compartments are also affected with different yaw angles, but not as much. So let's look at the effects of the train's height to width ratio with different wind yaw angles on the lift coefficient. So in other words, as we change the train's sleekness in terms of the height to width ratio, how does that affect the lift coefficient when we have different wind yaw angles? So this is shown in figure 11 here. So the researchers looked at each of the compartments separately and then the whole train together. In all of them, the effects of the height to width ratio only really affects the effects of the yaw angle on the lift coefficient when the yaw angle gets extreme, so above 60 degrees. Below that, the height to width ratio makes almost no difference to the lift coefficient when we change the yaw angle, or when we have different height to width ratios as well. When we get above 60 degrees, we see consistently that increasing the height to width ratio increases lift production. So we see here in case 1, that's where we have the lowest height to width ratio. As we go to case 3, which is the blue one, we get a significantly higher height to width ratio, which means that the train is a bit sleeker in that direction, and we get an increase in lift coefficient. When we get above, so we don't really have any surface pressure measurements for these cases, but so I don't know exactly the reason why this happens, but I think that the reason why we get an increased lift coefficient with increasing height to width ratio is because when we get more deflection of the wind, or when we get an increased height to width ratio, we get more deflection of the wind. So what that means is that the wind will jump over the carriage more, and that potentially results in lower pressure on top, and that results in more lift. I wouldn't be surprised if all the compartments, regardless of the height to width ratios, experience flow separation on their roofs because of the height to width ratio is quite extreme at around 2. But I think increasing this height to width ratio will result in more deflection of the air, which I think increases the lift. I think that's why we get a higher lift coefficient when we increase the height to width ratio at higher yaw angles. As I said, we don't have any surface pressure measurements or even flow vis, so I'm not sure if this is the exact reason, but I think this is what's happening here to get this trend. So for the side force coefficient, the train's height to width ratio didn't really affect it, even with extreme wind yaw angles. So we see here in figure 12, we have the side force, and regardless of the wind yaw angle, changing the height to width ratio makes almost no difference. And in fact, we get a few little outliers, which I think is mainly due to CFD error. So, and similarly with the rolling moment in figure 13, again, the height to width ratio doesn't make too much of a difference, and these differences I think would probably lie somewhere around the CFD error based on the CFD setup. So the researchers also gave the effects of the length to width ratio on the coefficient with different wind yaw angles, which we see in figure 14 here. So this ratio of length to width tells us effectively how pointed the nose of the train is, with an increasing length to width ratio meaning a more pointed nose. Interestingly, like the height to width ratio, only when the wind yaw angle increases to above 60 degrees do we see any real significant effects. In fact, when we get above 60 degrees, increasing the length to width ratio of the train's nose increases the lift coefficient. Increasing the lift to width ratio effectively makes the train sleeker at the front, which means that a sleeker nose increases the lift of the train at a greater wind yaw angle. So one thing I really would have liked to have more in this paper, or at all really, is flow vis and more surface pressure data. This is CFD, so that stuff is super easy to make, but alas, perhaps another time. So let's just recap what we covered in this podcast. We went through trains and how yaw angles affect the lift coefficient, the side force coefficient, and the rolling moment coefficient. And what we found was that as you increase the yaw angle, effectively we get a lot more differences in the lift coefficient with different geometries of the train. So if we change the nose geometry of the train and we keep the yaw angle at like 0 degrees or even 30 degrees or even 45 degrees, we don't really get much of a change in the lift coefficient or side force or pitching or rolling moment. But as soon as we go to like 60 degrees or higher, we then start to see differences with different train noses. And that tells us that the train nose is, particularly we need a sleeker train nose to like maximize the lift coefficient. And if we want to reduce the lift coefficient, make the train blunter at the front with different yaw angles. The problem with that is if we have a blunter train nose, generally speaking, we will get a higher drag. So that's the trade-off there. So with that, my little aerodynamicists, we come to the end of this podcast. If you liked it, make sure to give it a like. It helps us out a lot. And if you want to see more like this, click the subscribe button or the follow button, which will help you out a lot because you'll see more in the future. You'll get notified automatically. And if you want to get better at aerodynamic theory and or CFD, check out our courses in the link in the description where we go through stuff like this. So for example, in this podcast, I went through the CFD setup and where the strengths were, where some weaknesses were, and how to make this more efficient. We do stuff like this in our CFD course, so you can get better at CFD as well. And if you want to make your experiments 2 to 4% more accurate, get yourself an Atmosphere Hawk. It's an instrument we make to accurately measure the density of air. The reason why this is important is because the density of air always changes. For example, if you come into your wind tunnel in the morning, then come back after lunch, the density of air has changed by a few percent in just a few hours. It's amazing. That's because the density of air is affected by the temperature, barometric pressure, and humidity. And all these things do change all the time. So, we know when we wake up, it's colder. At midday it's warmer, and the barometric pressure fluctuates as well, as does the humidity. So for example, the other day I was at the office, and when I got there it was like a humidity of like 29%. It was very dry. Then when by the time I left, like because there were so many people now in there, like pumping out heat and like water from our mouths and sweat and whatever, the humidity actually went up to, I think it was like 55% over just a few hours. So that's how the humidity does change as well, especially if you have people in there. So having even in your wind tunnel area changes to the density of air because you are there means that you're going to have errors in your wind tunnel data. So what's more, the density of air changes even more than 2 to 4% between days, weeks, months, and seasons. So 10 to 15% changes are very normal, which means that you need to take them into account when you have your experiments. What's more, if you don't take them into account, then you are not only just getting random error in most of your experiments, a lot of the stuff you find is going to be in that random error, and you can't really be sure that what you're finding is true. Also, when you try to use this data for your CFD validation, you're going to have problems validating your CFD. You're going to have some things that will line up, other things that won't. In reality, nothing actually should be lining up properly because you have errors. And if they do line up, that's just fluke. And you can't really trust your CFD anyway. So you need to know what the density of error is in your experimental data so that you can then map that to your CFD and use the right density of error at least factor that in when you validate your CFD against your experimental data. That saves yourself a lot of headaches. So get yourself an MSC Hawk and make your experiments and CFD more accurate. You can find the link to it in the description below. And I'll see you next podcast. Peace, amigos.